Hey, now we're going to solve another problem here. So you have this function going from 0 all the way to square root of 2, okay? And the function is f of x equals square root of 2. So let's find the surface of revolution when this, or the surface of the solar revolution when this this function right here is going around, right, the y-axis. So now we have, it'll be 2 pi times the integral of the radius. Now what is going to be the radius? The radius is just the value of x, okay? For example, at this point in here, because what we have here is y equals f of x. We have y equals f of x. So you're going to be given the value of x. Since we're going around here, what is going to be the radius, for example, at this point? At this point, it's just going to be its value of x, because that's the distance between this point and the y-axis, okay? So it'll be x times the square root of 1 plus, well, let's check the derivative. The first derivative is going to be 2x. The first derivative squared will be 4x squared. So you put 4x squared in here, dx, okay? And we have to integrate that from 0 to square root of 2. 0 to square root of 2. Okay. So this is going to be equal to 2 pi times, I'm going to integrate this stuff, all right? And I'm not going to have to worry about this because it'll be simplified. So it'll be 1 plus 4x squared. It's to the half in here, so we're going to increase by 1 and divide by the new exponent. So 1 plus half, 3 over 2, divided by 3 over 2 is multiplied by 2 over 3. We do that, right? Divided by the derivative of the inner function here with respect to x, which is 8x. So I'm going to put 8 times 3 is going to be 24. So I'm just going to put a 24 in here. And here you have an x. But because you got to repeat this x in here, you're just going to simplify them, so don't worry about it. And it's just going to be this thing, right? From 0 to square root of 2. So we're going to have 2 pi, or 4 pi divided by 24. I'm just going to put pi over 6. And then it'll be, okay, it'll be square root of 2, right? X squared, you're going to put the square root of 2 inside the x, so it's just going to become 2, because it'll be square root of 2 squared, 2 times 4, 8, plus 1, 9. And here you have a 9 over 3 halves. But 9 is the same as the 3 squared, right? So you can say that it's 3 squared to the 3 halves. You multiply these exponents and you just cancel them out in here. So it'll be 3 cubed, which is 27. But hold on. Minus, and now we're going to do, and the pi divided by 6 is multiplying everything. So 0, right? So this thing is just going to be a 0. 1 to the 3 halves is just 1. So it'll just be a minus 1. So what do you have in here? You're going to have 27 minus 1, 26. So it'll be 13 pi divided by 3. Hold on. Which is approximately, the book says in here, approximately 13.614. 13.614. It'll be the area of this surface of revolution in here, but not counting this part. Okay, you're not counting the base, you're just counting this area here on the outside. All right. Okay. Now let's go to the next one. Now we're going to have some other stuff in here, a little bit of physics. Okay, definition of work by a constant force. If an object moves the distance d in the direction of an applied constant force F, then work done by the force is defined as work equals the force times the distance. So for example, if you have a box in here and you're applying a force, okay, of 3 newtons, for example, and you're moving this thing, this box, you're moving it like 6 meters, right? In the end, when the box gets in here, here in the end, what you're going to have is 3 times 6, 18, and it's called Newton meters, which is the same thing as joules. Now in the United States, for example, determine the working lift in a 50-pound object 4 feet. So the force is 50 pounds. Okay, I'm going to call LBS. And then you have the distance is 4 feet. Okay. So what you have multiplying these two is a force of, is a work. Okay, this is the work. This is also going to be the work. Work will be 200 foot-pounds. Just another unit. Okay. Okay. Now there's something else here. We're talking about Hooke's law. The force required to compress or stretch a spring within its elastic limits is proportional to the distance that the spring is compressed or stretched from its original length. So for example, let's just say that you have a spring like here and you want to compress it. Okay, I mean it's fixed in here and you can compress it or you want to stretch it. The force required, not the total force required, just the force required is going to be equals to K times D. So it'll be proportional to the distance from its original length times an elastic constant in here. Okay, and it depends on the spring, the material. Yeah, it depends on the material of the spring. Okay. So this is going to be the force. So for example, let's just say that from this neutral position, you stretched it up here. To keep it in here, you're going to have to be making a constant force in here, like force 1. Now you want to stretch it more. This is no longer here, now it's here. Okay, so to keep it in here, you're going to have to keep making a force in here, force 2, which is greater than 1. Because the K is the same, but the distance is going to be greater. Okay, here you have distance 1, and over here you have distance 2. So distance 2 is greater than distance 1, the force is going to be greater. Okay, there's something else called Newton's law of universal gravitation. So for example, if there are 2 particles, 2 masses, like one in here and one in here, the force of attraction between them is going to be equal to force equals some constant, okay, times the first mass times the second mass. For example, this is mass 1 and this is mass 2, is going to be this divided by the square of the distance between them. And it's the same thing if these are particles, like charged particles. So you have something here positive. If this one is positive, there's going to be a repulsion force between them. Okay, if this is negative, then they're going to attract each other, and there's going to be a force in there. So what is going to be the force in case of charged particles? You have F equals some constant times the first charge times the second charge divided by the square of the distance between them. Now, the value of these constants depend on the type of unit that you're using. Okay, if the mass for example, the mass could be, I don't know, in slug, it could be in grams, it could be in kilograms, the distance could be in kilometers, it could be in meters, it could be in, who knows, right? It could be in feet, inches. So the K is going to vary accordingly, okay? Because the K, what is the K? Well, the K is going to be the force times the distance squared divided by m1 times m2, right? You're just going to isolate K over here. So if m1 and m2 are in slug, the value of K is going to be 1. If the distance is in meters, the value of K is going to be another. If it's in kilometers, it's going to be another. So the value of K depends on the units that you're using. All right. Now, knowing that, that's a little bit of physics. You see, here's the problem. A force of 750 pounds compresses a string 3 inches from its natural length of 15 inches. So we're talking about pounds and inches here. Find the work done in compressing the spring an additional 3 inches. Okay? So, let me just... yeah, okay. So according to Hooke's law, you have F equals K times D. And it's saying that you need 750 pounds, all right? K, we don't know what it is, to compress a spring at 3 inches from its natural length of 15 inches. So the natural length doesn't really matter so far. It's being compressed 3 inches, okay? So you put the distance 3 in here. So we know that K equals 250. All right. Therefore, for this spring in this exercise, the force required, okay, is going to be equal to 250 times x. This x is going to be the distance from its neutral position. All right. Now, it wants to know, find the work done in compressing the spring in an additional 3 inches. Now, you see, what is going to be the work? All right, the work is going to be like this. For example, why is it kind of hard in here? Because when you have a box and you're pushing this box over here with a constant force, okay, of like 15 pounds, right? And you're pushing this like, I don't know, maybe 100 feet. So multiplying these two, you got 1,500 foot-pounds, right? Because the force is the same. But the problem is, you are doing a force of 750 when the spring is compressed 3 inches. When you compress it a little bit more, the force is going to have to be even greater. So you see, you're going to have to do the 3 inches, okay? But it's not going to be like F equals, the work is not simply work equals force times the distance. The distance is 3 inches, but what about the force? The force is increasing with every atom that you compress that spring more. It's increasing more and more and more and more. So how are you going to know what the work is? Well, here's the thing. You do work, okay, is going to be the integral, the total work is going to be the integral, okay, of the force, which is 250 times x times dx, all right? Why? Because you see the dx here is not just a dummy variable to tell you with respect to what this is being integrated to, okay? This 250, because you're integrating this, and the dx in here is just to show you that you're integrating with respect to x, right? Wrong. Okay, the 250x is going to be the instantaneous force that you have at a certain thing. For example, when it's 2 inches from its neutral position, it's going to be 250 times 2, it'll be 500, okay? So 500 here. And you're stopped. So far, as long as you're stopped, you don't have any work because you have to have some kind of displacement. So you're going to do, you understand what's going to be the work right there with an infinitesimal small or infinitesimally small amount of displacement. So what is this infinitely small displacement at 500? It's going to be dx. So it'll be 500 times dx. Okay, so you have 250x. That will give you the immediate, the instant force that's being applied at that point. But if you want to go an infinitesimal amount to the right and compress the spring just a little bit more, what's going to be the work right there as this dx in here goes to 0? This dx, guys, what is dx? Dx equals x approaching 0. Okay? Is it ever going to be 0? No, but it's going to be 0.000 infinitely zeros, and there's going to be a 1 in the end. So this is going to give you the immediate work right there when you are x inches from the neutral position. Okay? Now, let's just say that you want to do this work at that x, and the next x, and the next x, and the next x, all the way from 3 to 6. Then you integrate that stuff as the sum, okay? It's Riemann sums. I don't know if you remember that. Riemann sums, okay? So, the exercise is asking for an additional 3 inches. So you go from 3 to 6, right? So let's do that. So integrating that, you're going to get 250x squared divided by 2, 125x squared. Okay? From 3 to 6. Let me just, hold on. Okay. So it'll be 36, right? When you put a 6 in here, it'll be 36 times 125, which according to the book is 4,500. And then you have a minus 9 times 125. Which will be 1125, and this equals 3375 inch pounds. Because the distance was not in feet, was in inches, but the force was in pounds, so inch pounds. That's what you're gonna have to do this. Okay, you got it here. There you go. That's how much force you're going to need from 3 inches. See, at this point right here is just neutral, and then it gets compressed 3 inches here. This is 3 inches, and then from 3 inches you want another 3 inches, okay, which is down here. See? So what do you have to do? Well, you have to do 3,375 inch pounds of work, not of force, to complete this stuff. All right. So that's it for now.